If you recall, yesterday we included some more base derivatives. And our plan is to write down as many base derivatives as we can get through, and then the rules for derivatives. The rules for combinations of derivatives, chain rule, product rule, quotient rule, we're done with. Once we get those three rules down and then practice those three rules, all we need to do is add more base derivatives to throw into those combinations, and then do wackier and wackier combinations. And then as far as training goes, it becomes like a Fast and the Furious movie. It just gets more outlandish and more ridiculous as we pile on more combinations. But it's always the same stuff. It's just always the same stuff. So it just gets kind of more and more ridiculous. And then the villain from Fast and the Furious N joins the team in Fast and the Furious N+1. That's just part of the formula. I think if they make enough of these movies, some of us are going to end up in the Fast and the Furious movie, because we'll run out of professional actors. We're just going to get people to be in the movie. I do want to point out that at the time that Fast and the Furious 5 was coming out, I guess it was just Fast 5. It's just stuff combinations. It's like Street Fighter. They should just be like Fast and the Furious 2 Turbo Edition, and then just like Street Fighter. There's like 12 different Street Fighter games, but like the highest number is like 2. So, I don't know. I lost track. But at Fast 5, I said, you realize things are only escalating. This is before the movie came out, and I was telling my friends about it. I said, you realize by Fast and the Furious 10, they are going to be in space. I predicted that at Fast and the Furious 5 before it released. They announced Fast and the Furious 5 was coming out. They showed some clips from it. I said, oh, was that a fucking tank? Yeah, by Fast and Furious 10, they will be in space. Now, when did the Fast and the Furious team actually go into space? What movie was it? It was Fast and the Furious 9. But what happened? What happened between Fast 8 and Fast 9? Hobbs and Shaw happened. So I'll have you know that Fast 9 was, in fact, the 10th movie. And then I called my friends and I said, fuck, I was right. And they're like, oh, what are you talking about, Leach? You are the only person that you know that watches these stupid fucking movies. And I said, you guys are crazy. This is the greatest movie franchise of all time. So anyway. Oh, I'm glad I recorded that. I'm not going to edit that out because I stand by that statement. Fast and the Furious is the greatest movie franchise of all time. I am a Star Wars fan, but let's face it, Fast and the Furious is more consistent. What were we talking about? Oh, yeah. Quadratic stuff. All right, so I did want to make a note about associating this quadratic stuff with these trig functions. They all go together, but it's not just random. They go together for a reason. This is not going to help us remember or understand these particular derivatives. But here's what we want to notice. We want to notice that this 1 plus x squared goes with tangent. This is the way we want to think about this. This 1 plus x squared thing goes with the tangent. And we want to see why that is. It has to do with Pythagorean identities. So the 1 minus x squared goes with sine. I started saying sine when I was writing this word, so I started writing it. So one of the things I want to point out here is that these are the associations that I want to make. 1 plus x squared, that we want to think of that going with tangent. 1 minus x squared, we want to think about going with sine. And x squared minus 1, we want to think about going with secant. The reason that we want to make these associations and how it will help us remember these derivatives and eventually integrate things is Pythagorean identities. What's going on here is the Pythagorean, how these are associated with Pythagorean identities. So our main Pythagorean identity is cosine squared plus sine squared is equal to 1. This is our main Pythagorean identity. And what this means is that I can write cosine squared as 1 minus sine squared. So if I have a structure of 1 minus sine squared, I need to fix these to be thetas. I'm trading x's for thetas. Because I realize I'm about to substitute x for x, and that's always a bad move. It just becomes a scene right out of Being John Malkovich, and it's just very confusing. So the reason that we want to make these associations has to do with Pythagorean identities. I can write 1 minus sine squared as cosine squared. So that's what I want to have. I want to be able to write 1 minus sine squared as cosine squared theta. So where this might become useful is when I have that square root of 1 minus x squared. The problem with that structure is that I have a square root of 2 terms. I have an exponent being applied to 2 terms. And like we talked about before, exponents do not distribute over sums. This is a problem mechanically. This is just how numbers behave. I can't do anything with that. However, if I can replace 1 minus x squared 2 terms under a square root with just 1 term that's even being squared under that square root, now I can simplify. I can just multiply the exponents. So if I have a structure that says 1 minus sine squared theta, I can replace 1 minus sine squared with cosine squared and then simplify my expression. So I'd have 1 over the square roots of 1 minus sine squared So I've gone from having the square root of 2 terms to the square root of 1 term. And that is better. I can even simplify it. So through Pythagorean identities, I can mash 2 terms down into 1 term. Two terms, no. 1 term, yes. If this was a couple of years ago, I could have 2 pictures, those 2 pictures of Drake. There's probably a calc teacher out there somewhere still using that. And it's just as cringy as it was originally. I'm just kidding. You do you. Calc teacher who's still using Drake picture. I mean, who the hell am I to talk? I like reference the Matrix last week. Yeah, the fucking Matrix. That movie is like older than everybody in the room except for me. If you're the typical age for students in Calc 1, the Matrix to you is the Sound of Music to me. That's where it is in like the you are as far from the Matrix as I was at your age from the fucking Sound of Music. So anyway. So the point is that we make these associations because it's inconvenient to have something like the square root of something with two terms. If we can do some kind of shenanigans and get that down to one term, then we might be making our life easier. And then the Pythagorean identities, if we take this cosine squared plus sine squared equals 1 and rewrite that, divide everything by cosine, and I get 1 plus tangent squared theta is 1 over cosine squared or secant squared theta. And so we can see that 1 plus something squared can get pulled into one term through a Pythagorean identity. And so that's why the tangent, 1 plus x squared, goes with tangent. X squared minus 1 goes with secant, because if I rearrange this one, I can say secant squared minus 1 is tangent. So the idea is that we can use these Pythagorean identities with the proper substitution to get from two terms down to one term, because sometimes it is more convenient to have one term. This we're just putting out there way too early. This is foreshadowing for next semester. Next semester, we're going to be doing trigonometric substitution. Say, man, it is super inconvenient to have these two terms under a radical. I wonder if there's anything I can do. And you'll be like, oh, we could use a Pythagorean identity and some trigonometry to get those two terms down to one term. Then I'll forget that I said this. I'm like, oh, holy shit, that's a great idea. Let's do that. So I wanted to justify a few more things as far as derivatives go. Let's suppose that we want the derivative. I'm going to pick some of the easiest ones to justify. Also, they give us good practice with our new rules. So if we look at the tangent as sine over cosine, we know our trig identities. I know everybody knows all of our trig identities, all of them, like the double angle identities and all those stuff, right? But we definitely remember that that tangent is sine over cosine. So if I take tangent and write it as sine over cosine, now we get to practice using the quotient rule to find the derivative. So we're going to say that the top is sine x, and the bottom function is cosine x. So the derivative of the top, derivative of sine is cosine. I haven't justified these yet. You're all just taking my word for it, so thank you for that. And the derivative of the bottom is negative sine x. So those are the four pieces that we need for the quotient rule. Quotient rule says the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So let's use the quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom, which is minus sine, all divided by the square of the denominator. Now in the numerator, I have cosine squared plus sine squared, the minus from the quotient rule, the other part of the minus from the minus sign, the derivative of cosine is negative sine. So the derivative of tangent is 1 over cosine squared. And 1 over cosine is secant, so this is 1 over secant squared. I like this one, it's easy to justify. And it gives us practice using the quotient rule. We were introduced to, well, technically Friday, in more detail yesterday. Actually, no, I didn't do it at the problem yesterday. I just said, here's the quotient rule, and then just like ignored it again. The quotient rule is so mad at me. It's like, how could you treat me so badly? I am 1/3 of our 3 rules of combination. And I was like, oh, I'm sorry, what? Did someone say something? And the quotient rule was just sitting there flipping me off. So similarly, secant is fun to justify. That's right, I said fun. Secant is fun to justify because I can write this as 1 over cosine x. And you might be thinking, oh, we're going to do the quotient rule again. Quotient rule, right? No, that goes in the semicircular hole, right? Square hole. Actually, we're going to use the chain rule. And then I'm going to use the quotient rule. I'm going to do both. So one way to do this is to read this as a derivative where the top is 1 and the bottom is cosine x. So if we're really determined to use the quotient rule, if the top is 1, the derivative of the top is 0 because the derivative of a constant is 0. The bottom is still cosine x. And so the derivative of the bottom is still negative sine x. The reason that I'm doing quotient rule here is because earlier I had said quotient rule, product rule, chain rule, these things are always in effect. We just have to be careful of what our derivatives are. In this case, if the top is 1, then the derivative of the top is 0. And it just takes out one of the terms. You say the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom square. So in this case, we end up with sine over cosine squared, and that first term drops out. And I can separate this out into 1 over cosine x times a sine x over cosine x. And so 1 over cosine x is secant. Sine over cosine is tangent. We can use the quotient rule when one of our parts is a constant. We just have to remember that the derivative of the constant is 0, so it might be wiping one of those terms out. We can also read this as the derivative of cosine x to the -1. Notice that we can't write this as cosine to the -1 of x because then we've just written cosine inverse, and that is definitely not what the sine is, secant is. Secant is the reciprocal of the cosine, not the inverse of the cosine. So here, my inside function is cosine, and my outside function is to the -1. So inside is cosine. My outside is 1 over stuff. Or the way I'm going to read it, stuff to the -1. So the derivative of stuff to the -1 is negative stuff to the -2. Times the derivative of the stuff. So the negatives cancel out, and I've got sine over cosine squared, just like we had before. How's everybody okay? I told you that I threatened you earlier that eventually I was going to try to justify our base derivatives. At this point, you should be like, oh, you still have not dealt with this sine and cosine. When you point that out, I'm going to very noticeably ignore that comment and move on to the next thing. So there's the question. Here's the next thing I want to look at. So that's me ignoring that question. For e to the x, we're going to go back to our derivative. That's the one thing we had. Remember, we originally made this. We originally wrote down this derivative, thinking about the rate of change of an exponential function being proportional to the function, just a constant times the original exponential function. But here we want to look at the derivative, the definition of the derivative. So we'll take a look at the limits as h goes to 0 of e to the x plus h minus e to the x all over h. The reason that I want to do this is that some interesting stuff happens with limits, and we're new with limits, so we should see some of the interesting things that might happen with limits. And some cool stuff with exponential functions too. So here we are just doing delta y over delta x, and then making the delta y over delta x go to 0 over 0. Trying to figure out what 0 over 0 we're going to get. We know that we should be getting an e to the x because we already secretly know the derivative of e to the x is e to the x. How's everybody okay? I really look stunned. You all look like this. Still mad about the sine and cosine thing? I have to put that one at the very end so I can skillfully avoid it. That's called being a professional teacher. Leave the messy ones to the students to suffer with. Here's the reason I want to do this one. First of all, we want to notice some stuff about exponents. We've got e to the x plus h. A lot of times we know that we can take x squared times x to the third and write x to the fifth. It's a lot weirder to say x to the fifth is x squared times x to the third. I know it doesn't sound like it's weird to do that, but it is weird to do that because we're about to. E to the x plus h, I'm going to rewrite that as e to the x times e to the h. I'm just going to rewrite this term as e to the x times e to the h. Because when we multiply things with the same base, we add their exponents. And when we learn things in math, we have to learn it backwards and forwards. We spend so much time in algebra class putting things together, we forget that we can take them apart going the other direction. If it's more convenient to have x squared times x to the third, we can take that x to the fifth and break it apart. Now I want to look at the numerator and see if I've got a common factor of e to the x. I didn't need to write this way to see the common factor of e to the x. It just makes it more clear. So the next thing we're going to do is I'm going to take an e to the x out of the numerator. I'm going to factor out e to the x, and that's going to leave behind an e to the h minus 1 over h. Let's see what I did there. Nothing up my sleeves. Factored out the e to the x. Now what we want to look at is that e to the x factor does not have any h in it. There's nothing to do with the h in the e to the x. So now we're going to do something that looks a little bit suspicious. But this e to the x has nothing to do with h. So e to the x walks up to the limit as h goes to 0. So hey, I'm just the e to the x. I got nothing to do with this h business. Can I get out of here? And the limit's like, oh, get out. So I'm going to write e to the x out in front. Because e to the x is not involved with the limit as h goes to 0. I can pull e to the x out of the limit because e to the x does not have h. It's not part of the limit. We can pull e to the x out of the limit since the limit is about h, and e to the x has no h. As far as the limit is concerned, e to the x is constant because the limit is only concerned with h. Now we just have to evaluate the limit as h goes to 0 of e to the h minus 1 over h. Notice that when h goes to 0, I've got e to the 0 minus 1 over 0. I get that 0 to 0 over 0 form. I can't just plug in. I get 0 over 0. But 0 over 0 is not undefined. It's indeterminate. What value of 0 over 0 are we getting here? That's the question. So note that this limit is indeterminate. I spelled plug wrong. So if we just let h equal 0, we get 0 over 0, which is indeterminate. Since we have secret mathematical knowledge, we know the derivative of e to the x is e to the x. We know that the value of this limit should equal 1. So since we have secret mathematical knowledge, we know that the value of this limit must be equal to 1 because we know that the derivative of e to the x is e to the x. But to get at this limit equaling 1, we have a few options. We could look at a graph of the function e to the x minus 1 over x. We could look at some values of h that are close to 0 to evaluate this limit to see where we're headed. We can't plug in 0, h equals 0, because we get 0 over 0. So we plug in h close to 0. Or we look at a graph. So notice when we try to plug in 0, it's undefined, it's indeterminate, but undefined, same enough. But we are close to the values of 1. So it's clearly going to be going through 1. Any questions? Comment? It's not a remark. Graphs are great for visualizing limits. Yeah, we're plugging in values of h that are close to 0. So we can either plug in values close to 0 by looking at the graph, or if we didn't have a good graphing machine, we just grab our calculator and see what happens, like e to the 0.01 minus 1 over 0.01. And we would get values that are close to 1. Sorry, what again? So when h is close to 0, we're getting close to a value of 1. That's all we need to see. We knew that the value was going to be 1 because we happen to know that if f is e to the x, then f prime should just be this e to the x that we pulled out of this limit. Any questions? See, perfect timing. Now I don't have enough time to do sine of x plus h or sine or cosine of x plus h. If we want to use the definition of the derivative on sine and cosine, we're going to have to know our sine and cosine of a sum formulas. So sine of A plus B is sine of A times the cosine of B plus the cosine of A times the sine of B. So everybody remembers their sum and difference formulas, right? There's no quiz today on the sum and difference formulas. So does everybody remember their sum and difference formulas? Now you can say yes, because there's no quiz. There's not enough time. Like if there was like 10 minutes left, Michael, does everybody remember your sum and difference formulas for sine and cosine? You'd be like, well, I don't know. There's like enough time that you could try to find out. But like at this point, I'm like, oh, everybody remember sine and cosine, sum and difference formulas? I'd be like, oh, hell yeah, we do. Too bad there's not enough time for us to show you how well we know those things. Sum and difference of, what was it again? Sum and difference of sine and cosine. Hey Siri, what are the sum and difference formulas for sine and cosine? There's also going to lead to some weird limits once you pull things out. We're going to do the same kind of thing. Do some shenanigans, but there's going to be some sines and cosines with just x and not h that we can pull out of the limit. We're going to be left with some wacky limit that is going to be a 0 over 0, and we're going to have to know what value of 0 over 0 we're getting. It's going to be 0 or 1. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.